Good morning. We have been discussing boundary value problems. So far we have discussed linear and nonlinear 2-point boundary value problems. So, in case of linear, we have seen that the discretization leads to the linear system of equations, in particular tridiagonal system, which could be solved using Thomas algorithm. But in case of a nonlinear, we have observed that the corresponding nonlinear system could be solved using Newton-Raphson method. Okay. But so far we have considered only Dirichlet type boundary conditions, in the sense only the function values are given at the boundary points. So, now let us consider boundary value problems where the corresponding boundary conditions involve derivatives. So, definitely these type of boundary conditions play a vital role in the overall structure of the problem. Okay. So, let us see how far we can proceed with the derivative boundary conditions. So, BVPS derivative boundary conditions. So, let us start with an example. Say okay. Suppose, so the interval is 0, 1, h is 1 by 3. Okay. So, which means okay. So, now if we discretize this equation, okay, so we get, so usual central we have been using, okay, we get this, right. Then if we have to write this equation, strictly speaking, so these are the boundary points. So, I corresponds to 1 and I corresponds to 2 there. So, if we run for I equals to 1, then we get y 0, y 1, y 2 plus h square x 1 y 1. Okay. So, then suppose we run for I equals to 2, we get y 1 okay, right. So, in the earlier case we have seen where the corresponding boundary conditions are does not involve derivative terms. In this case we used to have y 0 and y 3, they would have been known. So, that y 0 y 3 are done and we have 2 equations in 2 unknowns y 1 y 2, but now the situation is entirely different. Okay. So, what is the difference? We do not have boundary values explicitly. We do not have boundary values explicitly. Okay. So, then what is, we have the corresponding boundary conditions which involve derivatives. So, one simplest solution could be, why do not we discretize the corresponding boundary conditions? Okay. Yes, for sure we can discretize. Okay. So, for example, consider this. Okay. So, this involve y 0. Okay. So, this means y 0 minus y 0 prime equals to -1. Okay. So, let us consider what could be the first order derivative approximation. Okay. So, the first derivative approximation, let us use central, this is second order approximation. Okay. So, it makes sense if you see this is a second order approximation. So, it is better to use for the boundary conditions as well. So, if this is the case, then y 0 prime, this will be y 1 minus y minus 1 by 2 h. Okay. So, what this is x 0, x 1, x 2, x 3 and y 0, y 1, y 2, y 3, but we have a term. Okay. So, we have, so this, if you think of this as x minus 1, so that means we have two equations I 1 2, but then we do not have explicitly y 0 y 3. Okay. So, then we have gone for the boundary conditions that involve derivative. Then if we discretize, we are getting an additional term. Okay. So, similarly, if we discretize at the other boundary, we may get another additional term. Okay. So, let us go back to general framework and try to discuss what would happen in general. Okay. Okay. So, consider more general derivative boundary conditions. Okay. Now, discretizing one, we have done it before. where so we get this. Okay. So, let us call this 3, right. So, we get, so now 1 I to n. So, if this is the case, 3 for I 1 to n involve y 0, y 1, y 2, it is very straightforward. We run I 1, it starts from y 0, then n we end up with n plus 1. Okay. So, this is a total of n plus 2 unknowns. Further, y plus 1 are not explicitly available. This is due to derivative boundary condition. Okay. So, however, we expect I 1 to n. So, n equations, but involve n plus 2 unknowns. So, still we have not used we have boundary conditions which are 2. So, let us discretize the boundary conditions. So, okay. So, with this at x 0, so we get this approximation. Okay. So, this implies a y 0 y of a and y dash of a equals to gamma 1. So, this becomes this is a 0 y 0 gamma 1. Okay. So, from this one could get y minus 1. Okay. So, let us write down a number, say this is 4. Okay. So, before we do anything, at x equals to, okay. So, y So, B 0 so this implies okay. So, these are different and correspondingly we have okay. So, 4 and 5 involve y minus 1 which are outside the interval a b. I mean which are outside the interval, which corresponds to nodes outside the interval, because nodes are x minus 1, x n plus 2. Okay. So, these are called fictitious values. Okay. So, let us from 4 and 5 one can express the fictitious values okay. So, the fictitious values have been expressed like this, but then unless we get rid of these two, we do not end up with unknowns equals to equations. Okay. So, what is the next step? Eliminating the fictitious values. If you recall, we have this equation which we were running from 1 to n. Okay. So, we were running from 1 to n. Okay. So, that introduced 1 to n. Okay. We have n equations, but discretizing introduced two fictitious values. Okay. Right. So, we have to eliminate. So, how do we eliminate? We assume that the discretized equation 3 holds for I equals to 0 and n plus 1, that is at the boundary points x 0. So, this is the alternative. Okay. So, accordingly I equals to 0. And we have y minus 1 from 6. Okay. So, we have to put it y 0 y 1. Okay. Coefficient of y 0 is b 0 and there is a coefficient here. Coefficient of y 1 a 0, the rest are known quantities. Okay. Say right, and I n plus 1 again we have 6 from that. Y n plus 2 we had. Okay. And from this we can collect the coefficients. So, one may ask what is the necessity of doing this general, one can solve any problem. Well, the answer is straightforward. Any numerical computation, we have to really set up thinking that we would implement on a machine. So, this kind of a general framework would help us, so that we could write the algorithm systematically. Okay. So, this is f 1 and say f 2. Okay. So, now we have 3 which is the system, and we have this F1 and we have F2. Okay. So, this will set the scenario with the number of unknowns equals to number of equations. Of course, 3 I 1 to n implies we get a big matrix so on so forth, and here we get this matrix, this big matrix, where n plus 2 unknowns. So, this is also a tridiagonal system and one can solve. So, when you have derivative boundary conditions, what is the rule? The rule is when you discretize the equation just leaving the end points. So, then we have only n equations. So, but then if we run the equations at the end points, then we get fictitious values. So, when we have fictitious values, what do? We discretize the boundary conditions as well, and boundary conditions also introduce fictitious values. So, now how do we eliminate the fictitious values? We eliminate the fictitious values between the boundary conditions and between the set of equations obtained by running the discretized equation at the end points. So, that the matter is settled with respect to the number of unknowns equals to the number of equations, and we obtain a tridiagonal system which we can solve using Thomas algorithm. So, let us solve some problem so that we understand much better. So, consider very simple case, and the boundary conditions derivative type only at one end point, just for simplicity. So, let us discretize the equation. So, this is, so we need to find out y 0, y 1, y 2. In this case, y 3 is given. So, we have y 0, y 1, y 2 are the unknowns, right. So, let us, so this is the equation. So, this is E B 1 B 2. So, this is discretization E I. Then B 2 this, then B1 I means discretized, that would give y0 this is y0 plus y dash this equals to 1. So, this implies two by 3 y0 plus y1 minus 2 by 3. Okay. So, this is F1. Okay. Now, let us run the equation I equals to 0. So, y so, from where we are running this, we had our equation okay. We had this. So, from here when I equal to 0, we get this. Okay. So, this implies plus h square x 0. So, this is 0 because of x 0. So, we get say this is E 0. So, E 0 and F1 eliminates y minus 1. Okay. So, this would lead to we have this would lead to we can simplify this. Okay. So, this is 2 minus 2 by 3, 4 by 3 y 0 minus 2 y 1. Okay. This 6 y 1 plus 2 equals to 0. So, this is one equation. Okay. So, this is let us say S 1. Okay. So, now I equals to 1, we get again from this when I equals to 1, so this we have h square is 1 by 9, x 1 is this. So, this will be this 27, 54. Okay. So, that will be minus so this is S 2 this implies okay. So, from S 1 S 2 S 3 implies okay. So, we have used y 3 is also 1. So, we have used that. So, this is gone. So, then we have 4 minus 6 0, then this is 1 1 0 1 we have minus 2 0 minus 1. Okay. So, one can solve this, it is a simple system. So, we get y 0 is minus point. So, the desired solution we get it. Okay. So, when we have the derivative boundary conditions we have seen, of course, in this example it is just one of the boundary conditions contain derivative, but if we have both as well, a similar procedure can be adopted. So, before we see that situation, let us go for a little bit of theory on the linear 2-point boundary value problems. Okay. So, some theory. So, we consider, we have seen already so this is our equation. Then we have not talked about, for IVP we have talked about existence uniqueness. So, it would be better to talk about the similar situation in case of 2-point boundary value problems. Suppose, so you say this, suppose f is continuous. F means of course, f given in star, the set suppose f is continuous on this set and that dou f by dou y and y dashed are also continuous on D if is greater than 0 for every this and to a constant m exists with less than or equals to m for every d. Okay, what is this? Suppose f is continuous on this set and both the derivatives with respect to y and y prime are also continuous on this domain. If this is positive and if there exists a constant, so that means if the magnitude of this derivative is bounded, okay, so then star has a unique solution. So, if you recall, we have for IVPs we have assumed Picard's existence, okay, satisfying Lipschitz condition, okay, and a similar sort of existence theorem for the 2-point boundary value problems. Okay. So, now let us consider in case of this form, okay. So, then we will have similar to what we have considered in the last lectures. Okay. So, then in case of this, if p x, q x, r x, they are all continuous on this and 2 q x is positive on A B, then double star has unique solution. Okay. So, now with respect to this uniqueness, we get little bit of idea. So, that means, if you have a initial value problem, we need Lipschitz type conditions, whereas in case of 2-point boundary value problems, we have a continuity as well as a positiveness and some kind of boundedness of the derivative terms with y dash etcetera. Okay. So, now if you observe for the linear 2-point boundary value problems without derivative boundary conditions, we end up with a, of course, even with we end up with the tridiagonal system. So, then under what conditions the tridiagonal system can be solved and things like that. Okay. So, let us see a little bit on that. Okay. So, we have say a special type just we consider where x belongs to this, okay, with y of a is gamma 1, y of b is gamma 2, okay, right. So, then when we discretize okay, and the corresponding boundary conditions. Okay. So, star can be written as j plus h square f on y equals to c, where, so we have already noticed that this produces a tridiagonal system, the entire thing, right. So, where j is of the form -2. Look at this, the coefficient of y I, okay, then the coefficient of y I minus 1, coefficient of y I plus 1. Okay. So, accordingly, so this we are giving it to f 0, then 1 minus 2 1 0, then 1 . So, we get this, and f bar contains f 1, f n, okay. Then then C would contain gamma 1, of course, okay. So, this is, we split it actually, y I could have plugged in, and we could have written this matrix in a different way, but I just put it like this, okay. So, which is a tridiagonal system. So, if the determinant is non-zero, then y equals to, that means is invertible, C, okay, and we get the solution from the tridiagonal system. Okay. So, this is with a linear case. So, let us see little nonlinear case. Okay. So, we consider Okay. So, there are several ones. So, I am just continuing, sometimes 1, sometimes star. Okay. So, then the discretized. So, what we use, because of this nonlinearity, we make a special remark. Suppose approximate 1 by a difference scheme of the form okay, subject to so that means these are some weights, okay, subject to these conditions. So, this entire thing has been approximated by this, but with a specific condition. Then the discretized equation can be put it in the form. Okay. So, the discretized equation can be put it in the form where again J would contain okay, then f of and B and alpha gamma 1 beta 0 h squared 0 okay. So, this system is so because we have f contains this, which is a nonlinear type. So, again one can solve Newton's method, okay, and similar conditions on this matrix holds corresponding to linear case. So, with this we have settled the matter for linear and nonlinear BVPs. Of course, there are other techniques as well, but within the context of finite difference methods, we discussed when we discretize the cases where we end up with a tridiagonal system, and even when we have derivative boundary conditions, how do we end up with a tridiagonal system. Okay. So, we will see so far we settle the matter only for second order linear 2-point boundary value problems. So, when we consider higher order what happens, we will see in the coming lectures. Thank you.